Let's talk about energy. It's very difficult to define energy and work without referring to the other concept in the definition. So it's a little bit circular, but it's difficult to avoid. Energy is the capacity or ability to do work. And work is the amount of energy that's transferred. It's the energy, the change in energy, if you like, the energy transferred by the action of a force. Let me give you some examples. If I lift up a box, then I'm working to lift that box up. If I let the box go and it falls, then gravity is doing some work. There's forces that are causing a change. But if I'm just carrying the box horizontally, then my lifting force is not doing any work because there's no change in the energy of that box because of my lifting. And gravity is doing no work because there's no change in the energy state of that box due to gravity. It's staying at the same height. So here, lifting up and down, work is being done. But here, moving horizontally, work is not being done. Now, of course, there is some energy transfer still happening. In my legs and other muscles, there is energy moving around and being transformed. So work, some chemical energy is being changed here. So there is some work happening, but there's no work with respect to gravity. The lifting here is not doing any work on the box. Okay, and that's important. We're looking at the energy change of the box, and there's no relative change in the energy of that box. If I'm leaning on a wall and the wall isn't moving, then no work is being done. Even though there might be a very large force pushing on the wall, there's no energy being transferred by that force, and therefore no work is being done. Okay, for the work you've got to have to happen, you've got to have energy being transferred. For example, though, if I have a box and I'm pushing the box along and the box moves by a certain displacement, then I can calculate the work as the force I exert multiplied by the displacement in that direction. Okay? The displacement in the direction of the force tells me how much work has been done. If my force and my displacement are not at the same angle, then I have to think about what this means in the direction of the force. This force is slightly upward, but the displacement is only horizontal. So I have to get the force in the same direction as the displacement, which means I'm going to be multiplying the force by the cosine of that angle, which gives us our formal description of how to calculate the work. Work is the change in energy. This is a Greek capital delta, which conventionally means changing. Work is the change in energy, the amount of energy transferred, and this is actually a vector dot product. It's the force vector dot the displacement vector. Now, if you haven't done enough vectors in Maths C or whatever, then it's force times displacement times the cosine of the angle between them. That's how you calculate the work. It's the force times the displacement in the direction of the force times the cos of the angle between them. Being a change in energy, it's measured in joules. And like so many other units in physics, it's named after a person, so it's got a little j for the name of the unit and a capital J for the abbreviation. 1 joule is 1 Newton metre, or 1 kilogram metre squared per second per second. So let's look at some examples. How much work is done by Jacob in climbing a 3-metre slippery slide ladder at a constant speed if he has a mass of 90 kilograms? Well, let me draw a quick diagram. Here's my slippery slide. Okay, Okay, it's a very rough diagram. That's perfectly good. It's 3 meters high. What is it? Why am I talking about a constant speed? Well, what that means is if I'm going to work out the work that's done, the work is the force times the displacement in the direction of the force. Now, the displacement's easy. That's 3 meters. But what's the force? Well, if it's a constant speed, the force I'm looking for is his upward force. But if it's a constant speed, his upward force is the same as the force pulling him down. And the force pulling him down is mass times g. That's his weight force. So we need to know its constant speed, so we know that the force upward here, this F, is the same magnitude as the force pulling down, which is mg. If it's constant speed, those forces are in equilibrium. Okay, so in here we're going to put mass times g, which is 90 times 9.8 times 3. Just give me a moment to find the calculator. Okay, 90 times 9.8 times 3. 2646. 2646 joules. Let's try another example. Braden lifts a 5 kilogram box to a height of 2 meters and then lowers it again. The total force of air resistance acting on the box is 4 newtons. Now, this is actually a pretty high force for just lifting a box up, but it's a number that's big enough for us to see what happens. Calculate the amount of work done by gravity. Well, if he's lifting a box up and then down again, and gravity is always pulling downwards, here we're working against gravity, so gravity's work will be negative, and here we're working with gravity, gravity's work will be positive. The net displacement is 0. And because the displacement is 0, therefore the work done is also 0. No work is done by gravity because the displacement up and then back again is 0. But what about the air resistance? Well, on the way up, the 2 meters going up, air resistance is pushing down against it. It's doing work. And on the way down again, air resistance is pushing up. Air resistance is still doing work. So the air resistance does some work. It's the force times the displacement in the direction of the force, which is 4 newtons times 4 meters, or 16 joules.